session is Sam Raskin. We'll continue on his lecture series on singular support.
Hi, everyone. So first, I wanted to start by addressing a question that I got somewhat informally after my last talk. So the question was, why not begin with some kind of roadmap that says this is what singular support theory is about, or something like this, which definitely was not the structure of my last talk. And so there's an answer to this question, which is that this theory involves, sort of several subtle constructions and distinctions, and some of these are a little bit abstract. And I wanted to try as much as possible in the last lecture to make apparent where those ideas come from and make them feel like the right set of constructions to be using for something. So that's kind of where that decision came from. Next, I wanted to address a quick correction. So this has nothing to do with anything, but there was this whole discussion with Bargov where I said in co of k of epsilon was equal to the DG category of flat, complexes of flat k of epsilon modules. And so this statement is true. And the statement I put last time was I ended up putting mod acyclic complexes, and that just gives you the usual derived category for kind of evident reasons. So anyway, just wanted to correct that once and for all. You can. Yes, yeah, sort of the DG category. Okay. Bargov tried to save me last time, and I didn't heed his warnings. So here we are. OK, so let me just kind of give a quick summary of what happened last time. So last time we said that if you had x, which was the vanishing locus for some function inside of some smooth y. So we said that if f is in quasi-co of x, or f is in int-co of x, then there are these natural maps eta from f to f shifted by 2. And we proved last time that f in int-co is perfect. Well, not perfect. Is in quasi-co if and only if this eta map is locally nilpotent. So the eta is locally nilpotent, which by definition meant that the direct limit of f shifted by 2n under these eta maps was equal to 0. So now I want to give a more general setup. So first I'm going to take okay. First, I'm going to generalize this just a little tiny bit. So first, let me suppose that x is equal to the vanishing locus of several functions. So for sort of f1 up to fr, let's say, is equal to 0 inside of y, which, again, continues to be smooth. So a generalization of last time. Is going to give rise to a bunch of maps, a to I, from f to f shifted by 2. I here runs from 1 to r. And again, these commute in some sense. So a to i's commute in some sense, which we'll make more precise later. And f is in quasi-co. Is equivalent to each a to I x locally nilpotently. So yeah, so sorry, is there a question? So this is just, again, a very mild extension of what we did last time. So now one thing that this already lets you do is something that came up kind of a little bit during the question session. So now let me suppose that in the same setup, I have n some projective variety inside of R minus 1 dimensional projective space. Yes? Well, I'm going to give a more general construction later on that maybe will pin them down in a different way, but they're again given by just sort of some canonical extension classes. Like, why are there R of them? Because there are R functions defining x. So what you should think is each one of these equations defining x gives you one eta I. Yeah. Other questions? So now suppose that I have some projective scheme, so it can be closed and can be reduced is fine. So I mean, nothing will be. It only depends on n as sort of a closed subset. So this gives rise to a subcategory in co sub n of x. In this case, and this is defined as follows. So this is so I can take I inside of k of eta 1 up to eta r to be the graded ideal that corresponds to n. And then this subcategory is where all eta i's, sorry, not eta i's, all, let's say, alpha inside of this ideal act locally, okay. It's sort of the set of F such that all alpha and I act locally nilpotently on X, on F. Another way to say this is that there's a canonical map of algebras from this k eta 1 eta r to the graded endomorphisms of F. So the direct sum of endomorphisms of F moving to its shifts by n. And I ask that some power of alpha lie in the kernel of that map. So it's a kind of typical support condition. So usually if you have a module over a ring, then asking that all elements in some ideal act locally nilpotently on the module is saying that the module is supported along the corresponding closed. And so I'm basically doing a version of that here. It's just that everything is graded because these eta i's are sort of saying cohomological degree 2. And so I only really get a reasonable notion when I deal with with projective subvarieties, with ones that are invariant under dilations. And so this is this construction of singular support in kind of a situation with coordinates, so to say. OK. So the next kind of goal is to generalize this to a setting without coordinates. Where I'll be more precise about what that means when we get there. So here we go. So in order to do that, I need to cover a couple constructions. So, yeah. Oh, yes. It's not. Yes, so you're right. So maybe I'll put that here. So just to have the picture, so this quasi-co of x, you're right. I should have said this later on. So this, the way this definition is set up is that we have an embedding like this, and this is actually equal to int co for the empty set of x, and this is equal to int co for all of p sub n minus 1 of x. Is that, yeah. Other questions? We'll maybe get back to that question in a little bit. So the, I guess maybe one way to answer that question is that last time when we proved this result, like up above, the way we used smoothness of y was that if you really kind of go back and look at it again, if you do this, the key fact was that if you take a coherent complex on x and you push it forward to y, you get a perfect complex. And that was what we ended up, that was the key fact that we used to prove this theorem. And so it really played a very essential role in having a result of this kind. Other questions?
In the end, is there going to be purely non-commutative characterization of the AIs?
Well, purely non-commutative. I mean that. Yes and no. Okay, so with that in mind, let's do some non-commutative geometry. So the first thing I want to talk about is what kind of somehow things are these A to I's. So I'm just going to sort of recall some formalism for discussing what kind of things the A to I's are. So I said, like last time, that the A to I's, the key property about them is that they're natural in F. So the kind of formal, so this is a sort of, okay, these are various constructions. So the scientific way to talk about like being functorial, being natural, and like for an endomorphism to be natural in the DG setting is the world of Hochschild is the language of Hochschild cohomology. So here, if C is a DG category, I'm going to set Z of C, by definition, is going to be the following. So it's endomorphisms of the identity functor for C in the category of sort of endofunctors of C. So end of C is going to be the monoidal DG category of DG functors from C to C. And so just to get a little bit of a feeling for this, so this, first of all, what kind of thing is this? So this Z of C is a DG algebra. And it actually has more structure. So using essentially the fact that my identity functor is the unit in this monoidal category under composition, you can actually see that the better Z of C is, so to say, an algebra in the category of algebras. So I'm omitting DG here. So these are what people sometimes call T2 algebras. And the key fact about it is that this implies, not key, but one consequence of this is that if you take the cohomology algebra of the Z of C, this is a graded commutative algebra. Yeah, and then just for words, this Z of C is called Hochschild cohomology. Of C. So how do we think about cohomology classes inside of, well, cohomology classes are sort of points inside of this Z of C. So what they are, like, let me think about this in the following way. So if I have a point in the Z of C, by which I mean, like, if you think in terms of real DG algebras, this is sort of a cycle in degree 0. But it's also, I mean, there's a way of converting complexes into simplicial sets, and I mean a point in that simplicial set, or in that infinity groupoid. So what's this eta? So let me just remind. So what this is endomorphisms of the identity functor. And so this eta gives me natural maps from F to F for every F in C. Well, maybe, I mean, so I'll rewrite it. So it's mapped from the identity functor to itself. And that's the same thing as giving, suitably understood natural maps from every object to itself for all F and C. And similarly, if I have some eta inside of Z of C with a shift by n, this is the same thing as a map from the identity functor to itself, but with a shift. And so similarly, I get maps F to F shifted by n for all F, sort of naturally. So the first thing is that, the takeaway of this discussion is that there's this thing called Hochschild cohomology. It's not so crazy, and also there's it's clearly relevant to our discussion. The kind of etas we produced last time, we should really be understanding them as Hochschild cohomology classes, or points maybe of Hochschild cohomology. And now, let me just say, in the case where, so kind of quick relevant example is that if X is a suitably finite scheme, so suitably finite DG scheme, so for instance, Noetherian would be fine here, then. Well, is that Z of X to equal Z of quasi-co of X? And under these suitably finite conditions, Z of X, Z of quasi-co of X is canonically isomorphic also to the center of int co of X. Where roughly the idea is kind of what we said last time. So if you have, if you have a point in here, so that's like a map from every quasi-coherent sheaf to itself, that also gives you a map from every coherent sheaf to itself, and then by some extension process, that gives you a map from every int coherent sheaf to itself, and there's a kind of converse that there's a kind of map going the other direction, which takes slightly more words to say, but if X is bounded from below, if the structure sheaf of X is bounded from below, then it's clear what to do. You embed perfect complexes into all intercoherent complexes. What was that? Yes, yeah. And it's because if I wrote HH dot, then people might wonder whether I'm taking cohomology, or so it's just it's kind of more unambiguous than writing something that would be like Hochschild cohomology, I think.
When you say endomorphisms for something like co and co,
For this, it's not relevant because it's like a non-continuous endomorphisms embed into continuous endomorphisms fully faithfully. And so endomorphisms of the identity inside of there, it doesn't really matter which one I take. Endomorphisms of the identifunctor. So it's like if you have natural maps from every object to itself, then you can recover those just by knowing those natural maps on compact objects by a kind of clear procedure. So that last sentence is just kind of saying it maybe a little bit more evocatively. OK, so that was kind of recollection 1. So recollection 2 is that there's what's called the Hochschild, so HKR equals Hochschild Rosenberg map. So this is going to be a certain map from something to something else. It's kind of implicit in the HKR theorem that such a map exists, and I don't need this whole HKR theorem in order to do what I want to do. So I'm just going to stick to the existence of a certain map. So this map, let me say where it goes, and then I'm going to kind of outline the construction. So so this HKR map goes from global sections of X with coefficients in its, I'll write the formula and then explain more. So here, Tx in quasi-co of X is the tangent complex. So I think Ben only talked about the cotangent complex, but this is just dual to the cotangent complex. So roughly what this says is that if you have kind of a first cohomology class with coefficients in the tangent complex, that gives you natural endomorphisms for every. Sorry, I had it backwards. Let me unwind that sentence and just not repeat it. So the claim is that there is some way of producing elements of this Hochschild cohomology, the center for X, from classes in the tangent complex. So that's what this HKR theorem gives you, or HKR construction. And now what I want to do is kind of outline where this construction comes from. So so for people, like we're kind of wondering what is, well, for myself, when I was learning derived algebraic geometry, I know that this construction somehow really impressed me, and I wanted to understand what it meant. And it was clear that to do that, you had to use ideas from derived algebraic geometry. And so I'm going to try to say it in a way that maybe isn't the most precise way I could possibly say it, but I only hope to communicate some kind of excitement. So yeah, so what I want to do is take my scheme X. So X is my really nice scheme. And so I'm going to form automorphisms of X. So this is, I don't want to be super precise about how I'm thinking about this, but this is some kind of group ind scheme. And this is sort of in the derived sense. So in the derived sense, I mean, in scheme, I mean like DG in scheme. So okay, I can put that. And X is a DG scheme. although this construction is already interesting if X is smooth or something like that. So I imagine that there's some algebra geometric object which parameterizes automorphisms of X. And whatever this automorphisms of X is, so the exact precise stuff here is going to turn out to be kind of irrelevant to the discussion, which is why I don't want to get too sucked into it. Now, whatever these automorphisms of X are, certainly they should act on quasi-co of X. And again, some sense. So if you have an automorphism of X, of course you get an automorphism of this derived category. So now, if you have, let me say, G, a group of DG scheme, or maybe IND scheme, there's a construction, so it doesn't really matter that G is a group. There's a construction called omega G, which is point. So here you take the derived fiber product, point times point over G. So this is a construction, so derived fiber product. So what you should do is, so you should think about this as automorphisms of this point inside of the scheme G. So it's a construction which is more familiar in the world of stacks. So if you, OK, G is a group, so it's slightly annoying. So if you stick with some stack and you have a point of that stack, there's some group you can extract from that stack. In usual algebraic geometry, it's the automorphisms of that given point. So for like B of a group, you would recover that group. In derived algebraic geometry, that works even for things that aren't stacky. So you end up with, like here, this is going to be something which is kind of physically a point if G is a scheme. But it's got some like lower cohomology groups. It's like there are terms that can enter into that Tor. So using that in this case, what you end up with is that omega, which was automorphisms, so omega of automorphisms of X, which is, so to say, automorphisms of the identity functor, of the identity point inside of X. So the identity automorphism of X. This is going to act on the identity for quasi-co of X. So, OK. I'm going to say this acts on the identity for automorphisms of X. And then by functoriality, this gives rise to omega of automorphisms of X acting on the identity functor for quasi-co of X. Now finally, if you pass to Lie algebras, then I'm going to get a map from the Lie algebra of this crazy thing I wrote down, this omega of aught x. So where does that map? So this Lie algebra is going to act on the identity. And that's the same thing as giving a map to endomorphisms of the identity, a map of Lie algebras in a suitable sense. And here, this is identity for quasi-co of X. And my endomorphisms are in where this lives, so this category of endofunctors. Endomorphisms of quasi-co of X, sorry. And the upshot is, let's identify the two sides. So first of all, this is, by definition, the center of X, this Hochschild cohomology for X. And now what's this Lie algebra? So the Lie algebra is, it's the tangent, in this formalism, I'm thinking everything is DG. So this Lie algebra is a DG Lie algebra. And it's the tangent complex to my group at a point. So this is the tangent complex to omega aught of X at its identity. And now if you just run this fiber product formula I told you, so you have a derived fiber product like this, And so like if you're trying to compute the tangent complex of omega odd x over the point, there's a canonical way to do that. It's the same as the relative tangent complex here, pulled back. And now if you use like the standard sort of 3-term exact sequence, what you end up with is that this is the same as the tangent complex for odd x with a shift up by 1. And finally, what's the tangent space to automorphisms of x? Well, certainly those are infinitesimal automorphisms of the scheme. It's like some Lie algebra attached to that. Certainly what it is global sections of x with coefficients in its tangent complex shifted up by 1. So OK, so that was a little. OK, so that gave the construction of this HKR map. So I guess there's a long book by Gates-Gorey and Rosenblum, which is about derived algebraic geometry. And one of the somehow major goals of that book is to make arguments along these lines precise. So that's why. So that's a fun thing you can try to understand if you want to learn this stuff, is actually like how do you translate all of this into rigorous mathematics. Another approach to constructing this, by the way, just for schemes would be, I mean, you can do it also by some kind of left Kahn extension and reducing to the case of polynomial algebras. So as in Ben's talks, you can reduce the construction of this map if you want to a kind of smooth case where you have so much rigidity that it's really possible to do these kinds of things. On the other hand, this is, I think, a nice sort of explanation for where it comes from. So again, just the principle is that automorphisms of x act on its category of quasi-coherent sheaves. So automorphisms of the identity in automorphisms of x act on the identity in quasi-co of x. And then you obtain this map by some differentiation from that. OK, so I'd have to think. Just I didn't think about it. Just there's different possibilities for what you could mean by tangent complex in the first place, like infinity versus simplicial commutative or something like this. And yeah, so mea culpa. And I'm also just like not up on the DG Lie algebra theory in that formalism. In the characteristic P setting, so I'm less confident answering. OK, so that was sort of point 2 on some journey, and now point 3 is I want to give a construction again in this sort of hypersurface case. So let me suppose that x is again this locus where f is equal to 0 inside of y. So here I'm going to give some kind of construction that, well, the goal of this construction is to tie everything together. So the way tangent complexes work is that, so I have the following fiber square. And then I get a short, so let me say this is I again, like last time. So there's a map from the tangent complex of x to the pullback of the tangent complex of y. And the homotopy kernel is the relative tangent complex, just sort of by definition. So this is a distinguished triangle, so I can kind of put it like this. So just as a kind of reminder that this is a distinguished triangle, I'll put the +1. And now, how do you calculate this relative tangent complex? So you can do it in the setting where you have a Cartesian diagram. It's just going to be the pullback of the relative tangent complex from 0 to a1. And now that, just like in these arguments over here, so you think, oh, there are no like kind of that relative tangent space should obviously be 0. But in fact, if you run the tangent complex, then what you end up with is the tangent complex for a1, which is just O, shifted up cohomologically by 1. So running a sequence like this, like exactly along these lines, but using the extra map sort of 0, A1, 0, will produce for you that this is going to be OX with a shift up by 1. So the pullback of the relative tangent complex here. And now this gives me an element on global sections, which is in global sections of X with coefficients in its tangent complex shifted down by 1. So either this map should be flat or X should be a derived fiber product. So the cotangent complex and tangent complex formalism, like you remove flatness hypotheses if you do DG schemes. OK, and now the key compatibility. If you tie all of this together, is that if you run the following construction, so here we have, so let's say X again is this locus where F is equal to 0, side of Y. So you have global sections of X with coefficients in Tx shifted up by 1. So this maps to Hochschild cohomology of X. And in here, I have a class in degree 2. So C gives me a class in degree 2. So that is a point of the complex, well, just move the shifts around. So there was a shift by positive 1. Here it's negative 1, so the 2 comes out over here. And therefore, it gives rise to a class in, well, OK, the compatibility. So key compatibility here is that C maps to eta in Z of C with a shift by 2. So last time we constructed this class eta, my claim is that it comes from tying all of these things together. So first of all, you have this HKR map that compares the kind of infinitesimal stuff involving the tangent complex to Hochschild cohomology. Then you have this particular construction for hypersurfaces of some kind of tangent vector in here. And if you run the degrees correctly, you see that, well, it's exactly in the right degrees, and claim the two things perfectly well match up. And so, what is Xi? Xi is here. Was that the question? What? So what produced that element is this. So here, I started with this exact sequence. Then I said that for base change reasons with the tangent complex, it's OX shifted by -1. That's the same thing as giving a map from OX to the tangent complex shifted up by 1. And that's the same thing as a global section of this complex. Does that answer your question? Okay. Other questions? OK, so that kind of covers the abstract approach, so to say, to what we did last time. But now the upshot is that sort of if you, so to say, remove the step 3, you get something which is kind of coordinate independent. So yeah, so now I want to give some kind of general construction that works in a coordinate-free way. So first, I'm not going to impose any hypotheses, and hopefully I don't 99% sure I'm not making a mistake here. So given this DG scheme X, there's some reduced scheme. So reduced, and this implies, so let me just remind, like the way derived algebraic geometry works is that all of the kind of cohomological stuff, like the difference between derived and non-derived algebraic geometry, those are nilpotents in a very precise sense. And so when I say reduced, this implies classical or non-derived. So this is going to be some reduced scheme. What was that?
He's complaining that you didn't write reduced classical.
Yes. So, right. I'm saying reduced in particular means classical. Classical is the same as, OK. Oh, I understand what you're saying. Yeah. So for instance, let me just say x is affine. Then this thing of x is going to be, by definition, spec of the direct sum over n even of the Hochschild cohomology group. So let me say h, or I can, OK, direct sum over n of h2n of z of x. So I said that the cohomology ring of this Hochschild cohomology is a graded commutative algebra. And so if I only take the even cohomological degrees, then I get some genuine commutative algebra. It makes sense to take its spec. And sorry, I'm going to take the spec, and then I'll just force this to be reduced by fiat. So I guess the kind of construction I'm going to give, yeah, and sorry, let me give one other piece of notation really quickly. So this is a graded algebra, and so it makes sense to take the projectivization of this too. So p sing of x is going to be, well, the usual thing. So proj of this algebra. Again, reduced. OK, so I think the construction I'm going to give next I could probably do in more generality, but I don't want to. So I'm going to give kind of a key example in which this thing is very computable. So definition, X, this kind of DG scheme with finiteness hypotheses, is so X. Really, I can say a finite type here. DG scheme is LCI, so locally complete intersection. It's also commonly called, for instance, in the Arinkin-Gatescory paper, it's called quasi-smooth. But that phrase is a little ambiguous, and well, anyway, LCI is evocative enough. If the cotangent complex of X, so here I mean the cotangent complex, is Zariski locally, let's say, of the form the cone, or if you want homotopy cokernel, of a map from P1 to P2, where Pi in quasi-co of X are projective, by which I mean locally direct sum ends of OX direct sum n for some n. So there's a key fact here which is easy to miss, which is that I'm not allowing shifts. So when I say projective, I mean like OX is projective, but OX shifted by 1 is not projective. So again, locally. Or if all of this is affine, you can just get rid of the locally parts. And so this LCI, well, let me kind of give a couple quick examples. So first of all, if X is smooth, which means in this setup that omega 1 of X is projective, that certainly implies that X is LCI. And in fact, let me just mark on a theorem. Probably, maybe it's due to Gitzker and Rosenblum, or maybe it's due to someone else. That certainly it's in their work that being smooth in this sense implies that X is actually classical, so that there's no ambiguity when you speak about smooth schemes, in characteristic 0. So smooth schemes, in this sense, recovers the notion of smooth schemes in Hartshorne if you're over a field of characteristic 0. That's not true for this LCI business. These LCI things, as we'll see in a second, can be genuinely derived schemes. So the second thing is that if X, so let me say Y maps to Z, and I take the fiber over some, well, maybe W. Okay. So if X is a fiber product like this, and Y, Z, and W are all smooth, that implies, so this is derived Cartesian, that implies that X is LCI. And that's by just a simple calculation of what the cotangent complex is for, for something of this form. So you can compute the cotangent complex of X over W. It's the pullback of the relative thing here. So that relative cotangent complex is going to be of the above form because Y and Z are both smooth. So it's going to, like the relative thing will exactly be a cone of such a map. And and then you sort of that's off from the cotangent complex of X by a copy of the cotangent complex of W. But again, that doesn't bother you. It doesn't kill the LCI-ness. And let me just kind of comment. So kind of useful fact is that if X is LCI, that implies that étal locally on X, well, étal locally X is isomorphic to 0 times AN AM for some F from AN to AM. And the last kind of comment here is that this LCI condition is very strong in the in some sense, it's very strong. So this cotangent complex, in principle, the way personally I imagine this in terms of complexes is that it's a complex in 2 degrees, -1 and 0, with it sort of has a free resolution of that form. There's sort of no reason that the cotangent complex couldn't go further down to the left. It couldn't have infinite Tor amplitude, and indeed that happens very easily. So it's a strong condition in that sense. On the other hand, if you just take some, let's say, affine scheme, some classical affine scheme, and you don't really care how you turn it into a derived scheme, well, your affine scheme can always be written as a non-derived fiber product like that, and so just turn it into a derived scheme by taking the derived fiber product. So that it kind of depends on the generators and relations that you chose for your algebra, but a kind of LCI structure does exist on any classical scheme, so to say. There's a derived scheme sort of upgrading your classical scheme, which is LCI.
Regardless of whether X itself is a scheme is LCI.
Exactly, yeah. But you're going to pick up negative, negative sort of cohomological generators in that case. So being usually LCI is being able to essentially to choose, coordinates like this where the map F is flat, so where there's no derived stuff entering in. Okay, so in this case, the space of singularities has a more concrete description. So the space of singularities of X, if you run it, it's going to be, so X LCI, and let me say affine. It's going to be spec of the symmetric algebra on H1 of the tangent complex of X. Sorry, spec. Say X classical coefficients in tangent complex of X restricted to X classical. And again, sort of, you should force this to be reduced. So this is a consequence of the HKR theorem, and it can also just be taken as a definition for us. So just to kind of orient you, let me just remind, the cotangent complex goes sort of towards negative degrees, and the tangent complex goes towards positive degrees. So here, when I take this tangent complex on X, if I restrict it to X classical, I get a complex with a sort of two-step projective resolution in degrees 0 and 1. And so this is the highest cohomology group in that case. This is kind of exactly measuring the way in which, like the H1 being non-trivial here exactly measures the failure of X actually to be smooth. Okay. So now, yeah, and let me also give some examples again quickly. So the first thing is that you should think about this space of singularities as being somehow analogous to the cotangent bundle of X for a smooth variety. So there, let me just note, like there's a couple of contravariant things going on. There you take the symmetric algebra on the tangent sheaf, and you take spec of that. And so the kind of functoriality properties of the space of singularities are going to be similar. So first thing is that if X, let me say that this is equal to y times v over 0, where v is the vector space. So finite dimensional vector space. And y is smooth. And I'm given a map from y to v from F. So in this case, the space of singularities of X actually embeds into X classical, X reduced, sorry, times V dual. And the construction we gave before, like essentially what it says is, well, the construction, this is encoding the idea that we said before. This kind of wraps everything together. So if X, you can think about this V as having a basis, so it's some kind of copy of AN. And then what I'm saying is that, out of this, you get like an n tuple of functions in that case when you choose a basis on the space of singularities. And so those are supposed to be certain classes in Hochschild cohomology, and that was kind of what the whole beginning of the lecture was about. It says that HKR, sort of at the derived level, is the symmetric algebra on the shifted tangent complex. Yes. So the singular locus, yeah. So this is some kind of, you should think about it as like a bundle, but not really a vector bundle. Like the fiber, it's like a, if you do spec of sim for, like this is a coherent sheaf on X. So up to that, it's supported at the singular locus of X. So at a smooth point, the fiber of this thing is just going to be like the point 0. So this H1, maybe another way to say that is that this H1 of the tangent complex is a coherent sheaf on X whose support is exactly the singular locus. Other questions? OX, yeah, sorry. Or X classical, really. So now I claim that if you're given some n inside of the projectivization of this singularity category, singularity space over X, so now, well, this really is a projective bundle with empty fibers over smooth points. This gives rise to a subcategory generalizing what we did before, this subcategory of sheaves with singular support inside of end co of X. And so let me give the construction. So it's just exactly what we said before. But now the upshot, well, kind of summary is that this works in the LCI case and not just in the sort of global complete intersection. So global complete intersection is when you're essentially of this form or something not so far, a fiber product of smooth terms. So yeah, so the construction is the following. So my n gives rise to a graded ideal. So I inside of this Hochschild cohomology of X. So H of Z of X, a graded ideal. And again, this inco of nx is the subcategory where the kind of operators in I, like the elements of I, so certainly homogeneous elements of I act locally nilpotently. So first, let me give a claim. So again, just kind of to orient yourself. So first example is that if n is all of piecing of x, then int co sub n is equal to int co. So it's, so to say, covariant stratification. Another example is that if n is the empty set, then I claim that this int co of sub n of x is exactly equal to quasi-co of x, naturally embedded into int co as we discussed last time. And let me just kind of very briefly sketch the proof. So you reduce to the global complete intersection case. So the case where, for instance, X is just explicitly a fiber product of this kind by some étal localization. And there it follows from what we already said. OK, and so that, well, it's 3 o'clock, so so that concludes the lecture. So just and that maybe slightly less awkwardly. So OK, this was the definition of coherent singular support, which is what the lecture series is about. So again, there's this singularity space in the LCI case that like if you take this projectivization over X, you get like from subvarieties inside of there, you get subcategories of int co that are kind of like as the subvarieties get bigger, your sheaves get worse and worse. Is the somehow principle. The homological algebra of the sheaves get worse and worse. So, OK, thanks. And
We'll have time for one question or two for Sam. All right.
So if you take n not to be reduced, you get the same answer as for the reduced thing.